So I'm going to give a brief overview of what ESF has been doing on your lake, or at least what my laboratory in ESF has been doing at your lake. For those of you on Zoom, the very last slide will have my email address. Feel free, if you have questions, to just email me and ask questions and stuff like that. I get quite a few questions like that. So it's an easy way to exchange information. I do want to point out that this is a partnership. There are a lot of different people working on it, and that boy, PhD student here, is actually here in the room. But there are other people, Bofan, Sarah, Sydney, etc., that are working in my laboratory that do a lot of work behind the scenes that you don't see. So we can just go to the next slide. Just a very, very quick overview as to what harmful algal blooms are. They're caused by a cyanobacteria. The picture in the middle is actually from Lake Tai in China. It was one of our study sites. I just think it's a really pretty picture of how bad things can get. That's a brick, by the way, sitting on the shore. The important thing to know about cyanobacteria is that they're a very old species. So they've been around for about 3 billion years, which means that they're at their peak of evolution, which means that if you give them food, they will know how to use it because they've had 3 billion years to figure out how to do anything that they want to do, right? So don't think of them as a primitive species. Some float to control how they interact with light. Some can use nitrogen out of the air. Some form blooms, some form toxins, some don't form toxins, and they're a very diverse group of organisms. Okay. The question everybody here has is why blooms form, and I wanted to take just a minute to review this. They basically need 6 things. They need a source of food, that's nutrients in the form of nitrogen and phosphorus. They need light because they're a plant, so they are photosynthetic. They need the water to get warm enough, so you're not going to see a bloom once the ice comes onto the lake. They control their buoyancy with these little internal life preservers, and they float up and down in the water column to control how they interact with light. But that means if it's a really windy day and the water is really mixed, you can overwhelm them, and so the blooms don't float to the surface, right? They need a seed population, and then there's these crazy interactions with zebra mussels, which you have a lot of in your lake right now, and so we'll do that. The reason I point this out is that they need all 5 of these things. And so we may be working on nutrients, but if the lake isn't warm enough, the bloom doesn't happen. Or if the lake is too windy, the bloom doesn't happen. And so it becomes very complex sometimes to figure out what you did and what nature did in terms of why the bloom did or did not show up at any given time. And sometimes we think we're having a tremendous effect when in fact nature is actually controlling what's going on with this whole process. Okay. The next question is, well, how do we prevent the blooms? Well, you can't do much about the seed population. They're there, and zebra mussels are there. So we're not going to really be able to do much about that. If you flip to the next slide, neither can we do much about light, temperature, and wind. So there are some things we can do in terms of mixing the water column in a localized area to prevent a bloom at a particular site, but you can't do that on a lake-wide basis. So that brings us back to nutrients. And I want to emphasize this. We spend all our time talking about controlling nutrients, but just remember, nutrients aren't the only thing that's important. It's just the only thing we can do anything about. And in terms of nutrients, they need primarily nitrogen and phosphorus, but these guys are equal opportunity offenders, so they don't really care about the source of nitrogen and phosphorus. If it comes from the creeks, fine. If it comes from the sediments, that's fine too. If it comes from decaying plant material, that's fine also. If it comes from a sewer runoff, that's fine also. If it comes from your septic system, that's fine also. And so our job is really to try to figure out, well, what's the relative contribution of these different things so that we can figure out how to optimize any type of management plan or approach. Because we don't really want to spend a lot of money fixing source A if it's really just not that important in the grand scheme of things. All right. So what are the long-term trends in Cazenovia Lake? The nice thing about Cazenovia Lake is you guys have a really good monitoring program that's been part of CSLAP for many, many years. So there's a lot of historical data. And you'll see the blue line there basically shows that the phosphorus going back since 1988 is sort of bouncing around between 10 and 20 micrograms per liter, or 0.01, 0.2 milligrams per liter, depending on how you want to put the numbers. The red line there is actually, I'll talk about that, that's what's happening down in the deep waters. And you'll notice it was really high back in the 1995-2000, and later years it's dropped down, so it's approaching what's in the surface water, and I'll talk about that. So your phosphorus concentrations on a big picture don't seem to be that high, but you're still getting blooms. So the real question I'm interested in is, why are you getting those blooms and what's driving those blooms? So, next slide, please. All right. So we actually have 3 projects going on. One of them is to look at, well, what's happening in the deeper waters and how important are nutrients in the deep waters to Cazenovia Lake. The other one is to look at non-point sources, or creeks and tributaries. Now, Cazenovia College is doing the tributaries and the creeks, so we're not going to duplicate their efforts there. So we're looking at other potential non-point sources that are much harder to measure, things like lawn runoff and septic systems, and I'll talk a little bit about that. And then finally, to go back into the idea of, well, what is, or who are the cyanobacteria that are actually growing in your lake, and what are the different properties and things like that, and how can you be involved in that? So I'll talk very briefly about these individually, and then you can ask me some questions. Okay. All right, internal sources. Just to review, you have sediments at the bottom of your lake. Those sediments, as phosphorus comes into the lake, it settles down into the end of the lake, bottom of the lake, and normally that phosphorus gets tied up with minerals and is pretty stable at the bottom of the lake. However, if the bottom of that lake runs out of oxygen, those minerals will release the phosphorus back up, and then it can mix back up into the upper part of the lake where the algae are. The algae can't grow down deep because it's too dark. Trust me, I've been diving down there on the buoys. It's pitch black. There are no algae growing down there. There's usually a division between the upper and the lower part of the lake. That's called the thermocline, and that's a temperature stratification that serves as a barrier. And one of the first questions we had is, well, how strong is that barrier? And does it mix over the course of the year, or does it actually form a really strong barrier? So over the last 2 years, you'll notice we have had a buoy sitting out off the boat launch, and that buoy has a series of thermometers basically hanging on a string that goes down to the bottom. For cost reasons, we don't do the data in real time, so you can't go on the web and see what the temperature is that way, but we do download it at the end of the year, and we generate a map. So next slide. So this is the temperature map for the last 2 years in Cazenovia Lake. The upper part, the warm red temperatures, are warm temperatures. We're up in 24 to 26 degrees. But the blue is the colder temperatures, and you'll see that there is a very sharp thermocline that's formed in this lake, where the bottom layer is very cold and the upper waters would warm up very nicely. And I don't have an example here, but you'll see that the thermocline is very stable. It's not breaking and mixing top and bottom, etc. If you look on the one for 2020, we had to pull the buoy a little earlier because it got hit by a boat and decided to go cruising around the lake on its own. But in 2020, that was 2020, in 2021, you can see we got the buoy in before the thermocline actually set up. So you'll see on the left side, the water is cold top to bottom, and then the thermocline establishes, and you can't really see it on this, but we fortunately pulled the buoy right after the thermocline started to break again. So on the far, far right side of that one, there's a thin blue line that goes all the way up to the top. This is exactly what we were trying to do. You'll notice the thermocline differs between years. Some years it's deeper than the other and stuff like that, but it's very sharp. If that thermocline, the blue waters, goes anoxic, then you potentially have a lot of phosphorus being released into that lake. The interesting thing from our point of view is we managed to have an oxygen probe down there in 2020, and we think the thermocline is going anoxic. But if you remember the graph I showed of the phosphorus concentrations, whether you're measuring the phosphorus in the deep water from sea slab, we're not seeing that phosphorus. And so basically the data is not what we would call internally consistent, right? We think we should have a lot of phosphorus, but we're not seeing it. So that means we're going to have to do it again next year. We're going to do it next year anyway, but we now have even more reason to have to do it next year. So we'll put oxygen sensors down there next year to see what's happening, right? The good news though is that thermocline is pretty stable. It's not breaking, so it's not serving as a source of phosphorus during the growing season. Whether it's probably remixing at the end of the year, that's a slightly different question. So to look at some of the other sources of nutrients and trying some relatively new technology, we have a boat. You've probably seen it. It's got chemistry at ESF stamped on the side. It's pretty obvious. It drives around the lake very slowly at about 5 miles an hour. And what you can't see in the front of that boat is a whole ton of scientific instrumentation. So we're sucking water up into the boat. We're running it through a whole bunch of different sensors, and we're trying to measure all sorts of crazy things like turbidity and temperature and how much algae is in the water, how much laundry detergent is in the water, etc. Laundry detergent is a really good marker for septic systems because you put these optical brighteners in your laundry and it goes right straight through your septic system. So this is just some of the boat tracks that we did in last year. I know they're small, they're a little bit hard to see. On the one side, the left side, this is just colored dissolved matter. This is brown stuff that leaches out of wetlands and things like that. And you'll see is similar to what you saw in the frog bed study that up on the north end of the lake, there's a lot of brown colored water that's coming in off of the swamps and wetlands and stuff like that. Much less as you get back. The little green spike that's sitting down there is where Ann took the boat and did a little slight divergent to go out to the buoy to do some buoy work and then come back. The sensors were running at that time, so it shows up on the map. On the right side, we're seeing some of the laundry detergent markers, looking at some of the septic systems. And the first thing you'll notice if you look on the north end of the lake, you'll see the red in both cases. This is bad for us because this says that the dissolved organic matter in there is interfering with our ability to actually measure laundry detergents. And so, you know, that's life, that's science, that's research. We've got to figure out a way to solve that. We've got all winter to do it before we have to go back out next year. So we have a few things that we have to do done. I put two inserts in there that are along the east side of the lake, right? And you'll notice on the left side in the insert, you'll notice that that's green all the way along the shore. That's the CDOM. However, if you notice on the right side, you'll see that yellow sort of spot in the middle. That's the type of stuff we're looking for because that says that we have a signal in our septic system marker that's not coming from colored dissolved matter that's coming off the wetlands and things like that. And so areas like that we need to go back and look at again. We get the same pattern next year, etc. And then we figure out what the source of that potential signal is. And so we're using some of this new technology to try to track down where these sort of non-traditional sources are of phosphorus coming in. And finally, the one that I think is most fun is looking at the different algal populations that are happening in this lake. And this is done in collaboration with Bob Crichton. We have something that's called an iolite microscope that Bob has. It's linked to your cell phone, and so you put a little drop on the microscope, the cell phone takes an image, picture of the microscope image, and then you mail it off to someone like me who does the microscopic identification. And it's very interesting because we know that the types of blue-green algae are changing in your lake. I know DEC basically says you have a blue-green algal bloom, but there's only about 8,000 different types of blue-green algae. There's only about 100 of them that we're really worried about. So it's really important for us to know who is actually doing the bloom. And in this particular case, this happens to be a particular type of blue-green algae that is not associated with toxin formation, but is very good at getting nitrogen out of the air. And so we're very interested in these types of blooms to see, you know, where they're occurring. Are they being driven by just phosphorus and things like that? And I like it because even though the DEC would say you have a blue-green algal bloom, you can immediately go into the, you know, not toxic concern, right? And so we don't worry about some of these blooms nearly as much as we might worry about some of the other ones. And the nice thing is this can happen in real time and very rapidly. Assuming that I check my email, I can usually get a response back to whoever sends the image within, you know, 24 hours, you know, stuff like that. The other one that we have out there is, we know we can't be there for all the blooms, so we're playing around with some autonomous monitoring systems. And so these are telemetry units that actually float underneath people's docks. We have one on the central buoy also, and that is constantly monitoring your water for algae, for temperature, conductivity, and turbidity. It's linked to a cell phone system, and then that cell phone basically broadcasts it back up on the web, right? And what you see there on the left-hand side is sort of Anne put together a summary of where blooms have been reported from 2013 to 2021. You'll see many of those blooms are non-toxic, i.e. there are no toxins associated with them. A lot of them are those Dolichospermum that we were interested in. But some of them do actually have toxins associated with them. A little harder to see, but there you'll notice there are 5 stars on that map, one at the yacht club, one at Bob's house, the center buoy, and then 2 along the west side, right? These are where we have the in situ, the permanent monitoring stations. And so those systems are constantly broadcasting back. And if you go on to the Cazenovia Lake Association website, they probably have the link of how you can sit at home and look at that data when we put it back in. We pulled them for the winter, obviously, because we don't want them sitting there under the ice, but we'll put them back in probably next April and things like that. You can do that, right? So you can monitor the data yourself. You need to write CLA to get the web link because the web link is like 40 million characters long with all sorts of absolutely crazy things. And so there was no way I was going to write it out on a website. It would be an entire slide. Stuff like that. Okay, so that's just sort of an overview of what we're doing. We'll just open it up for questions. Like I say, for those of you who are, this picture of Anne in the middle, sitting on the dock working on one of the constant monitoring systems, that looks like the Yacht Club one. And then that's the picture of the boat with chemistry at ESF. If you see us out on the lake, feel free to stop us, especially if I happen to be around, because I always like to sit and chat. The students actually have work to do, so they try to work. But I'm always happy to sit and chat and explain things, and talk about what we're doing, and things like that. So anyway, I'll just stop there, throw it open for questions, whatever.
So here are the 2 slides here, the one that you're going to kind of watch next year, the optical brightness.
Yep.
That was like right on the village-town line. So you're suspicious that they're making, because that's a sewer area too.
Yeah.
So I'm just wondering what.
Yeah. Well, it could be optical brighteners. I mean, we like to say that it is due to laundry detergent because that's the most common source, right? But there are other things that it could represent a stormwater drain. It could represent a creek inflow where somebody has a septic that is actually flowing into the creek and it's going down. So, I hate to be too specific. We have to get more detailed and go back and look at those places. But honestly, the first step is to go through, find them, and then go through and find them again and see if you can find them twice. If you can find them twice, then it's worth going back and trying to actually look at them and try to figure out what it is.
Can the contribution be beyond the water's edge, but because the topography is very steep there, like Wright Road area? where it could be transcending the waterfront.
It could be.
To the-
One of the problems we have is doing it by boat is that we can only get so close to the shore, right? Without banging up the prop too many times on rocks, which does happen. So yeah, and so it could be coming in from lawn runoff, for example. It could be coming in from underwater flow and stuff like that. And so once you identify these, then you actually have to do like the frog bit people. You got to go back with a canoe and get in really close and try to see, you know, if you can sort it out. Right? So the question is basically there are a number of chemical approaches. Just to give you a background, a little bit of background on this. So the best thing you can do for harmful algal blooms is prevent their occurrence. And so we're really focusing more on prevention. There's a second series of things that we're working on, not on Cazenovia Lake, which are called mitigation. This is, you have a bloom, you want it to go away instantly. What can you do to treat that bloom and make it go away instantly? And so we've been working in several other lakes working on mitigation. The problems with mitigation is that you have to be careful that you mitigate the harmful algal bloom and not mitigate the fish and the zooplankton and everything else that's in the lake that you want. And so there is actually a couple of studies that are going on. One using hydrodynamic cavitation that we're involved. This is where you mix the water up and you create nanobubbles and things like that. We can talk more about actually how it works. The problem is that it's very site specific. So you could treat a swimming beach maybe, right? But you can't treat a lake the size of Cazenovia Lake. It's just a lake, it's too big for where the technology is right now. You guys have used chemicals before, copper sulfate. Those of you who follow the news know that Skinny Atlas Lake, because it's a drinking water supply for Syracuse, just got a new permit for copper sulfate, and it is extremely controversial, right? Copper sulfate, first of all, goes in the sediments and it will be there forever. It never goes away. So you have to be really careful if that's, you know, that the cure is not worse than the problem and stuff like that. We've talked about putting mixers off the swimming beach to just drop the water column to give short-term relief. That's certainly a viable option. Sodas Bay takes their, for example, de-icers that they use to protect their docks, and they turn them on in the summer, put them sideways just to mix the water, and it's very effective about getting rid of the blooms. But it comes back to, you know, in that real early slide is if you don't get a bloom, was it because what you did, or was it because nature just decided it wasn't going to have a bloom this year and stuff like that? So yeah, we can talk more about that. I don't think Cazenovia Lake is at the stage where that would be appropriate, but you know, things could change.
Greg, I'm still seeing some algae blooms. Even yesterday I saw one down at our property.
Yeah.
And the water is, I think, pretty close to 50 degrees. Are they cyanobacteria?
Yep,
or are they...
probably.
Okay.
They're probably. Delicospermum, you know, we like to say the water has to drop below 50 degrees before the blooms start to go away, but we've done under ice studies in Neotawanta and near Fulton, and they'll hang around in water colder than that. They just don't really grow very much. And so what you're probably seeing is remnants of blooms because we have these nice sunny days that are washing up on the shore. But they're probably not really growing and multiplying.
They still potentially be toxic?
They could potentially be toxic, and we still have samples that come in from different lakes. This has been a very unusual fall in that it stayed very warm and very sunny very long. And so we had a lot of blooms that showed up in late October when we would traditionally, you know, this is one of the things DEC may have to rethink their when is the end of the season. Those of you who work with the DEC website noticed they shut it down last week, basically saying the HAB season is over. And a lot of us are saying, ooh, not for me, stuff like that. So, yeah.
This summer and this fall, we've had so much rain, the level of the lake tremendously deeper than I've ever been in a while.
Yeah.
Does that have any effect on what you're talking about?
Absolutely. So the question is, does all this rain have all this effect? The problem with all this rain is, remember, these guys don't care their source of nutrients, so all this rain is associated with a lot of runoff coming into the lake, and it's bringing a lot of nutrients into the lake. This late in the season, the question becomes, what happens to those nutrients? If you remember back in 2017, when they had rainy season early in the year, those nutrients washed into a lot of the finger lakes, like Skinny Atlas lakes. The algae sucked them up, and then they sat and waited for conditions to get good for them to grow. So they took the nutrients up early in the year, and then the blooms happened later in the year as the weather warmed up and became bright and sunny and calm. You have the nutrients washing in late in the year, so they could just go sit in the bottom of the lake. I mean, they got to go someplace. So some go through the outflow, but a lot of them just sit in the bottom of the lake, and they could potentially be an internal source next year. Or the algae might have taken them up, or the plants might have taken them up, and they might just sort of dissipate, right? They came in, they get flushed out, through the outflow, and they don't have a real big impact. And unfortunately, we won't know that until next year, exactly what's happening.